תודה רבה לעורך דין יורם הכהן. אני מתכבד להזמין את רלף לנגנר שיקח אותנו באחת לאזור מערכות הבקרה התעשייתיות. רלף לנגנר התפרסם כמי שחשף ופיצח את סטאקסנט, אז בבקשה רלף.
כבוד גדול.
כן. There you go, that's yours.
Thank you very much, I'm flattered. Ladies and gentlemen, let's get physical. I would like to share some insights, some experiences from the perspective of somebody who does the real thing as I protect industrial facilities against cyber attacks for a living. So let's just begin with some very basic stuff. What is cyber-physical? A cyber-physical attack causes physical damage by manipulating bits and bytes. So what's very different to your average IT attack is that the cause of your problems is in cyberspace, but the consequence, the effect, occurs in physical reality. And that consequence could be the physical destruction of equipment. It could also be, for example, the release of toxic substances. So I'm going to talk about cyber terrorism also in a minute or so. And there is certainly one big difference to your average IT attack, and that is for disaster recovery. You can't just recover your stuff from the backup tapes. So it's not virtual, it's real. You will see destroyed equipment, damaged equipment, and in order to recover, you will need to have the capability to step back in time. Obviously, that doesn't work, so you have to suffer real physical damage. Now, how is that possible? I would think that many of you are under the impression that's kind of magic. And certainly there are many people around there, especially in the hacker universe, who actively suggest that they're magicians, but they're not. So it certainly follows the basic rules of logic and programming. The major difference to your average IT attack scenario is that you need to attack what we call a cyber physical system. And the majority of those systems are not computers. That appears to be a problem for many people. So just to give you an idea, you have heard something about SCADA already. SCADA is just the tip of the iceberg. SCADA is the exception where you actually see computers, usually running the Windows operating system. But most of our bigger problems are completely unrelated to computers and to the internet and to TCP/IP networks. So most of the real critical systems we are dealing with are called PLCs. They are called, for example, IEDs. We are dealing with valve positioners. So probably acronyms that you haven't heard before, but believe me, those are the real critical systems, and you won't see an Intel chip running inside these systems, and you won't see the Windows operating system. You probably won't even see a network interface. But again, those are our major concerns, the very critical systems, because they are at the forefront of physical reality. So they are the point where the rubber really meets the road. And certainly for your attacker, that's the best target that you can dream of. So IT really doesn't matter that much, and I strongly suggest to you that you discontinue using the phrase SCADA security. I suggest to use control system security, because SCADA always implies computers. It's about a supervision of what's going on at the cyber-physical level, and your hardcore attacker would simply bypass your SCADA system and go directly to the controllers, which, by the way, is what also happened in the Stuxnet scenario. So the SCADA system really was used only as a distribution mechanism for the dropper, and the real significant stuff occurred on the controller level. What you see here, I've brought a cyber-physical system with me, so what you see in the picture is a very good example. What you see there is a protective relay that you would find in power plants. And I'm pointing this out because this is a typical system that usually nobody from the IT department sees, touches, or even gets near to, because you must be a certified power engineer to configure that system. And unfortunately, our power engineers don't understand a lot of stuff in terms of cybersecurity, and that's something that needs to be changed. Another very interesting thing I would like to point out now, these two protective relays, as you can see, they have an interface, but it's not a network interface. It's what we call an MPI interface, and as a matter of fact, you could actually use the Stuxnet exploits to get code running onto those relays. And if you're clever, you would manage to destroy a power generator. Here are some examples for targets that you could hit with a cyber-physical attack. And I see three major groups of targets. So certainly you would try on a nation-state level to hit military targets using a cyber attack. I cannot imagine any future war that would not have a cyber component. So certainly your adversary nation in a kinetic exchange would try to disable some of your weapon systems, some of your reconnaissance systems with a cyber attack. I would take this as a given, but I won't focus on this very much. The next level in the middle that you see is what's usually referred to as critical infrastructure. So all the targets that are also needed for civilian life in a modern society, like the power grid, like water, or like transportation. So these also make for very good cyber physical targets because you find those control systems almost everywhere, and as you have already heard, there is very little protection. This is something that your attacker is interested in. And last but not least, something that's most of the time that's forgotten, I call those dirty targets. There you see, for example, chemical plants that process hazardous material, or nuclear power plants, or hospitals. You would probably, your attacker wouldn't be interested to attack your nuclear power plant if you had one in Israel, not to disrupt electricity, but to release radiological substances to turn your nuclear power plant into a dirty bomb. And so these are targets that we don't expect to get hit in a real war between nation states, because there are international treaties which would prohibit anybody from attacking those targets. But certainly terrorists didn't sign those treaties, and they would probably have some wet dreams about blowing up a chemical facility somewhere in Israel to cause casualties. So this is the major distinction. The targets in that lower section, when you hit them, you can actually cause casualties. And I'm not talking about just 1 or 2 injuries, but I'm talking about, let's say, several hundred people would die. I think it's a sign of limited imagination that we, in the past, when such scenarios have been discussed, most of the scenarios that we have seen were doomsday scenarios, where via a cyber attack on your nation, your attacker would dramatically wipe out everything you have with cyber. So they would bring down the whole power grid, and they would cut off your water supply, transportation, everything. So, for example, if you think about scenarios like Dark Angel by the US government, I guess that was 2002, that's a good example. And in my opinion, I don't see that as highly realistic. I believe there is another problem that we are faced with today, and that's the problem of instability and criticality, and what is meant by that. I'm concerned about cascade effects. So, if you need to protect a high-value target, your job doesn't end at making sure that nobody blows up this target. What you really need to do, your aim is that the security of your target is not threatened. Let me give you an example. For example, in the nuclear industry, when we secure a nuclear power plant against a cyber attack, the idea is not to prevent somebody from melting the core. The problem starts when somebody messes up your security or safety. That's already your problem that you must prevent. So you have to guarantee that your safety and security posture is not compromised. In a nuclear power plant, if that happens, for example, you discover that some of your backups or some of your emergency preparedness systems is no longer operational, you have to shut down the power plant. And in many cases, this is even done automatically. Now, if we transfer this to national security, it's more difficult. Because if you discover a cyber threat against national security, you can't just shut down the nation. So you have to deal with that in a different manner. So what I see here is, so the problem that we are facing is not the doomsday scenario, where a catastrophic cyber attack would just bring the company, the nation to a halt, but a staged sequence of events. And that might begin with a limited but coordinated cyber strike against, for example, the power grid, where you would see limited outage, coordinated with an attack on a water system, probably also coordinated with an attack on a chemical plant. And what you get there is then you got some physical and biological effects, so people will probably die. You can't hide that. It's obvious for the media. You will be on CNN big time. So the effects are visible. And that will certainly trigger some psychological effects, some economical effects, and probably even strategic effects, because your ability, your military ability might be affected also if you take down power plants, for example, that are also required by barracks or other military facilities. That certainly affects your strategic posture. So we will see a couple of indirect effects, and I just predict that this will also be a dam break for copycat attacks. I predict that many of your adversaries will say, whoa, that's possible? Somebody really managed to bring down a power plant in Israel via a cyber attack? Hey, that's great. Let's also try to do that. So you might see a terrific increase in offensive cyber budgets among the usual suspects. We might see terrorist organizations focusing on educating their eager young males in cyber and cybernetics and control systems, rather than how to use equipment for a suicide attack. And so this, again, I predict that this will, so even a barely successful cyber strike will have a dramatic impact on a global scale. And certainly there will be some kind of response, so there will be a political response, and ultimately there might even be a military response. So it could be that you, or if you think about the United States in that scenario, you might respond by a kinetic attack. I would even say this is highly likely. It's, as you will know, it's even official, the official doctrine of the United States Department of Defense, that if they suffer a cyber strike of some significance, they will strike back using kinetic weapons. Now, the point is, that might just be what your attacker wanted to provoke. Because, as I will explain later, we are not just talking about nation states as adversaries, we are also talking about terrorists. That might just be what they have in mind. But I guess the major problem is that at some point in that curve, there is a threshold, which I call the criticality threshold. From there, you enter into a crisis. And the problem with that threshold is that from there, you no longer have control over the situation. things can get out of hand. If you're lucky, they won't, but you just have to bet on your luck and on your best effort. And this is certainly something that you don't want to see in respect to national security. So from that criticality point, from that threshold here, you see this cone is opening. If you're lucky, you end down here, and if you're not so lucky, things might actually come to a doomsday scenario that all of us want to prevent. So I believe the major focus should be to the bad enough threshold, so where things could start to get out of hand. This is certainly something that I in my work tried to prevent. This must not happen. This is my goal. I mean, when we are right here, we have lost already. So what is one factor that might get you there is the problem that obviously cyber and cyber warfare seems to be difficult to understand compared to kinetic weapons. A kinetic weapon is very easy to understand, both for the attacker and for the victim. So if you look at that gun, you understand what that means. You understand what the impact will be if that weapon is fired. You understand that as the attacker, and you also understand that as the victim. Unfortunately, in cyber, that's not so easy.
You've just been attacked.
This is physical attack. Right, physical attack.
Easy. Is it yours? No.
No.
Is it yours?
No.
No.
Somebody just erased my presentation.
Saudian hacker.
Did I say something inappropriate?
It's okay. It's,
Thank you very much. So we try that again. Sorry for the interruption. With cyber, it's not so easy. It appears that cyber is difficult to understand, mostly because it's abstract. So you don't know, or it's difficult to tell what's going to happen when you just look at a USB thumb drive. And everybody in this room is aware of what can happen if you put a USB thumb drive into the wrong system, right? Now, I would like to stress one thing here. I would like to get back to a remark by General Hayden. It's actually a homemade problem because, you know, cyber didn't grow by nature. If you don't understand what's going on, it's not nature's or God's fault. It's your own fault. And this is something I'm working on very hard to educate people. Well, you can understand that. If you don't understand that, that's your own fault. I'm sorry, but I have to tell you this. It can certainly be understood because it all adheres to the rules of logic. It is possible to understand this, and it's absolutely required for defense. But as it happens, most people really don't have a clue of what's going on, and therefore we can see that the fog of cyber war is much bigger than the fog of war. Just to give you some examples here, all the items that you see here in that foggy distance, they have all been claimed to be potential targets of the Stuxnet virus. So, for example, the Deepwater Horizon disaster in the Gulf of Mexico, or problems with an Indian satellite. There was even a well-known cybersecurity expert in the United States who claimed, well, we may never know what the target would be. Just imagine, I'm just bringing this up for you to imagine if this was an imminent crisis. So you would just have discovered you are under cyber attack. Your national infrastructure, critical infrastructure, is under cyber attack. And you would certainly hear all kinds of rumors what this would be, either on local television or on CNN and throughout the internet, what this would be. And here is another example of the fog of cyber war. What you see here, these items have all been theories of the attackers behind the Stuxnet attack. Somebody said that this might have been France, and others said this might have been Greenpeace. And by the way, I'm not talking about idiots or jerks. So those statements all came from well-respected experts. For example, a DHS official said in a hearing before the US Senate, well, that might have been done by a botnet operator. And again, that other US cybersecurity experts said, we may never know who did it. All this in an imminent crisis might just put additional fuel into the fire. Another problem that's typical for such a cyber attack, a US government cybersecurity expert warned that the Stuxnet virus could become more menacing because it could morph into a new threat. Well, let me tell you something. I have that thing in my lab for 2 years now. It didn't morph. I really have a hard time understanding how somebody with obviously some technical background would say such nonsense. But so it is nonsense. But you're going to hear all those things when a significant cyber event happens, this is something that, as I said, that will put oil into the fire. Bottom line is, one problem that we have to address right now is that the whole cyber war issue is surrounded by magic and secrecy. So many people want you to make you believe that it's really magic and that they have capabilities of a magician, so they can strike any target that they want, and you can do nothing against it. Well, certainly that's nonsense, and I'll try to explain why. And there is another problem, that's secrecy. Secrecy is not nonsense. I'll also explain why this is a tougher issue to deal with. But these are two very important characteristics of the cyber discussion that we are leading right now. So let's try to break that down. Let's try to put the fog away. On a technical level, it can be shown that depending on the attacker's capabilities, which you see here in that arrow to the left, the attacker can achieve different levels of attack complexity. It is very, very easy to disrupt a process by attacking those cyber-physical systems because they are, well, let me just put it this way. The security posture of any of these little boxes that you have seen is much, much lower than the security posture of any laptop computer that everybody is carrying around here. As a matter of fact, most of these systems don't even survive a simple Nmap network scan. They just crash. That's a known fact. And so if you're just a lazy hacker, you can attack those systems very easily, and you can cause disruption. But the problem is with that low-level stuff, you won't be able to reach anything of significance, and your results, the effect, will be non-deterministic. That extends only barely above this level where you get process control. So the only thing that your average hacker could do is to stop the process, but again, you really wouldn't be able to predict what's going to happen. But hackers would be able to cause some problems. If you have some insider knowledge and some engineering capabilities, you would be able to really control the process. And this is much easier than many of you think, because, for example, many people are under the impression that in every industrial facility, things look completely different. That's nonsense. It's just not the case, because guess what? the industry is using standardized products. We have a set of big players in the market. For example, if you look at power plants, you have companies, vendors like Siemens, General Electric, etc. Just a handful of companies who are the suppliers. And if you have understood their products, you can basically manipulate any power plant, for example, that would operate the GE software or the Siemens distributed control system. And then at the very top, we have the capability to disguise. And this is where nation-state capabilities would come in, because this is very, very tough. And we have seen that in the Stuxnet scenario. But most people don't understand that you really wouldn't need that. It depends on your scenario. It depends on what the attacker really intends to achieve. If I am your attacker, I might not be interested in disguising the attack. I might want the world to know. I might want to take credit for it. Just think of a terrorist organization. If you would see a cyber strike against Israel, I would predict that probably 5 to 10 terrorist organizations would claim credit for that on the same day in the news. So that really depends on the scenario. And you don't need those capabilities on a nation state to create a high amount of damage. That's also a big misconception. In the Stuxnet scenario where disguise was used heavily, this was not used to maximize the effect. It was used for a completely different purpose, to make Iran believe that they were not under a cyber attack, that those were the average problems that they used to see, but just on a higher level. So if somebody tells you, well, Stuxnet failed because it only managed to destroy 1,000 or so centrifuges, well, that wasn't a failure in that sense, because the idea behind Stuxnet was not to destroy as many centrifuges as possible. And it's not that General Hayden told me or Amos. It's just you can see that in the attack code. The idea was not to cause maximum damage. It was to make the whole attack very, very stealthy, to make Iran believe they are running into so many problems that they just wouldn't manage to get those centrifuges running on a large scale. So talking about capabilities, at the very high end, what we have seen in Stuxnet, we have seen around about 15,000 lines of payload code, scientific process knowledge, and even a fully functional mock-up of the Natanz fuel enrichment facility, which really amazed me, because I must infer that the code was test-driven on an operational IR1 cascade, because we see that some of the attack routines require process gas, so they must have been filled with uranium hexafluoride. That's the very high end that only nation states can do. At the low end, you can see, well, 4 lines of payload code, like you can see here. Last year, I did a proof of concept. So I was interested in if you have understood the Stuxnet attack and you wanted to boil that down to the minimum level that would guarantee you some kind of damage, this is what you end up with. 4 lines of payload code, and those 4 lines work generically, so they would just stop every Siemens controller that this code is running on. And stopping it, I must explain this, it's not that, okay, then your process is put to a halt. No, the thing is, with that attack code, it just freezes the controller. It freezes the program, and that means in this case that what we call the outputs, the actuators, stay running. This is a problem. This will almost certainly result in some material damage. And you can achieve that with 4 lines of code. That's not a really big deal. So, talking about scenarios, you have all heard the phrase digital Pearl Harbor. And I just used this picture of the Pearl Harbor Memorial with the USS Arizona here. I don't believe this is very realistic, or that this should be our highest priority or highest concern. I think we should more be worried about cyber Cobra towers or a cyber Lockerbie, or a cyber label. So I'm referring to state-sponsored terrorism, because this is, for me, this is much more realistic than an all-out cyber exchange between nation states. Here is another picture of a cyber physical system. And as you can see, it looks just like a sitting duck. That's amazing, isn't it? Well, in fact, those systems behave like sitting ducks. It's just a fantastically static target, because in those facilities, you don't have a dynamic environment. You have heard that already in previous talks. Once that these systems are commissioned, they won't be touched for many, many years. And it's a common phrase among engineers to never touch a running system. And so certainly your attacker could try to take advantage of that. And another big difference to the IT world is that your vulnerabilities are not bugs, they are features. They are designed into those systems because nobody thought about cybersecurity. Everybody thought about accessibility and convenience. So don't be surprised to see many, many thousands of completely vulnerable systems. They are just like sitting ducks. And just to give you another idea, the vulnerabilities that had been exploited by Stuxnet on the controller level, they were there for more than 10 years. They were just staying dormant for more than 10 years. And you know what's the most funny thing? They are still there, even after Stuxnet. So they didn't get patched. They are still there. And I believe that somebody should really start to get serious about this by saying to the vendor, well, you know, we just can't use those products anymore until you fix those vulnerabilities. So all this given, how do you defend? I was quite surprised to see a big discussion on offense being the best defense. So as I have mentioned earlier, for example, the United States is officially saying, well, we deserve the right to hit back kinetically. So what's the best strategy? Should you just rely on your conventional force? Should you build something up like US Cyber Command and strike back digitally, or would you probably need some kind of an Israeli version of the DHS? So now I come back to the secrecy issue in order to give you my idea of what would be the best strategy for defense. What you see here are two conflicting statements. The first statement says critical vulnerabilities are classified so that they won't be exploited. This seems to make some sense if we don't tell everybody that our systems in critical infrastructure are completely vulnerable. Probably the bad guys won't notice and won't attack us. Okay? The second statement is just says the opposite. Critical vulnerabilities are classified so that they can be exploited. Well, you know, the difference is the perspective from which you see this. The lower statement is seen from the offensive perspective, whereas the upper statement is from the defensive perspective. So, as a matter of fact, there are significant forces in governments who make sure that the critical vulnerabilities remain classified so that they can be used in future attacks. And as an example, we have seen that in 2007 in the United States. The DHS launched an experiment which was called the Aurora Experiment, where it was demonstrated how to blow up an electrical generator using a cyber attack. And this still is classified. I can only show you this because at some point in time it was leaked. It was, for example, there is a video that was aired on CNN showing the generator blow up. But the funny thing was the people who did the experiment, I can say this because those are my friends, I know them personally, they had some significant trouble on their job. Actually, they got fired. And at the end of the day, the whole problem was that some other agency within the US government was working on the same vulnerability for offensive purposes. And as you have heard a couple of times today, offense wins. So offense is more powerful, and this also happened in this respect. So unfortunately, the Aurora vulnerability, which is really significant, is not addressed on a large scale as of this day. But the thing I would like to point out with this is that vulnerabilities and attack vectors are kept secret because protection is possible. This is just an evidence that protection is possible. So it was classified because everybody knows, well, there is a fix for this. And if our potential adversaries apply that fix, we can no longer use that weapon. But what does that tell us? As another big difference between kinetic weapons and cyber weapons, in the kinetic world, protection might not be possible. If you think about nuclear weapons, for example, you can use a nuclear weapon to attack any kind of target in any country, any location. And no matter which protection you might have in place, you really can't protect against the blast of a nuclear explosion, which is why your offensive deterrent capability is extremely important. With cyber, it's completely different. With cyber, especially in the cyber-physical domain, protection is possible and often even straightforward. So you could say that the cyber-physical battle space is created by the lack of protection. That's the opportunity you are offering a potential aggressor. It is even sometimes straightforward. So what you see down here, this map, this is from a research by Aaron Leverett, which he talked about earlier this year in Miami at the SCADA Security Scientific Symposium. And you can, the talk is online, so there is a video recording. You can check that out. And basically what Aaron showed, that it's very, very easy these days, just for example, to locate control systems that are exposed to the internet. And you can even put that into Google Earth, and all those nice symbols here, those represent control systems which are exposed to the internet. Now, I would say that if you are stupid enough to actually expose a critical control system to the internet, you probably deserve to be attacked. That's your fault. So if something bad happens, it's not the attacker's fault. There are bad guys out there. Well, no surprise, isn't it? And so this is something that's really, really stupid and that you shouldn't do. Everybody can use a search engine on the internet. It's called Shodan. Just go to shodanhq.com. It's publicly accessible, and you can search for control systems. So. To finish up my ideas, at the end of the day, you might ask, how secure should you be? And I believe there are a couple of thresholds that need to be observed. So right to the right, again, I have tried to symbolize the attacker capabilities. If you want it to be totally secure, you would need to protect against extremely sophisticated cyber attacks by nation states, and just like, for example, US Cyber Command, CIA, etc. That will certainly be very difficult. Then you would be totally secure. But I have to make this point. There are areas where you can be totally cyber secure. For example, coming back to nuclear power plants, one big problem that we have in the nuclear realm is that there are digital safety systems out there. So there are vendors who use digital technology for your reactor safety system. And certainly this offers an opportunity for a cyber attack. But there are other vendors, other products that are analog. So if you just don't use digital and use analog instead, you can be totally secure in this regard. It's just, in some places we see much more cyber systems than we would have to see, just because it's done out of convenience, which is also the case in nuclear. But on the other side, to the left, you see a typical system, typical security posture. And what you can see here, it's below the dumbass threshold. I think that's important. That tells you that even a dumbass would be able to cyber attack your system. That's not a good spot to be in. Just to give you an idea, I guess 2 years ago, a hacker attacked the HVAC, so the heating, ventilation, and air conditioning of a hospital. I guess it was in Texas. And this is very easy. And this hacker was stupid enough to record himself doing it on video and posting the video on YouTube. A couple of days later, the FBI knocked on his door and arrested him. But again, so this was proof of concept. Even the very stupid guys can do something like that. And so this is not a good place to be in. I think where you really should be is about here. You should try to be secure enough. And how do I get to here? Because there is a second threshold which I think is extremely important to cross, and that's the threshold where you get beyond the capabilities of non-state actors. I mean, this has been discussed earlier today. I would not bet that our usual suspects on the terrorist side will continue suicide attacks for decades to come. At some point in time, they might realize how cool cyber warfare and cyber terrorism can be. And again, I think this, if the first cyber attack happens either against Israel or the United States, this is going to be a landslide. Our usual suspects will divert substantial resources into building up that capability. And it's not, you really don't require the resources of a nation state to really hit hard. And so you should be above that. You should make sure that a terrorist organization who would either build up cyber capability on their own by having some students who study, for example, in Germany. We have a lot of Arabic students over there who study cybernetics and automation technology. But sometime some of them might turn rogue. I don't want to see that happen, but it might happen in the future. And you should also take into account that there will be, or probably still already is, a black market where you will be able to purchase a very decent cyber attack against critical infrastructure. I would assume that probably around about $5 million would buy you a really decent cyber attack against power plants or water facilities. So you should be above that threshold. And the next threshold that I see, and that's important for nation-state adversaries, there is a reliability threshold. So even in situations where you can't say I'm 100% secure, what you still can achieve is take the reliability out of the attack. So your adversary cannot bet on striking you on December 1st, let's say at 3 a.m. in the morning. Probably they might succeed, but they cannot count on it. And in a military scenario, that certainly makes a very, very big difference. So what I am aiming at in my work, I try to cross that reliability threshold, that if I have to take into account nation states as adversaries, just to be such a pain in the ass for the attacker that they will say, okay, just let's look for a different target. Just don't try to attack those facilities which are protected by RALPH. Okay, thank you very much.